I decided to split this piece off from the other video, here I'm just going to talk about the photoelectric effect. Right. This is one of a number of experiments that contributed to the widespread acceptance of the idea of photons in the early part of the 20th century. This one is relatively simple to understand, I think, and it also is chemically useful because it tells us some things about different elements. All right, let's venture into this. The reason for talking about these experiments, by the way, is just that the idea that I want you to think of light as being made up of these little increments of energy like that, that's very non-intuitive, right? You have no perception of that as a macroscopic world person. It's worthwhile looking at the evidence to see how did we get to believe in this idea? Why do we think this is a sensible description? Right. So here's the experiment. I start off, I've got a piece of metal down here, and so this represents just a metal plate of some sort, right? That metal is just going to be in a vacuum chamber, and then I'm going to shine light on it, okay? So the red arrow there suggests light from some source coming in. I want my light source to be so that I can control its wavelength. And so nowadays, if I were doing this, I might use a laser or something fancy like that. If I was in the early part of the 20th century doing these experiments, I would have had to be more resourceful and use maybe a very bright arc lamp and shine it through some filters to pick a wavelength. But we control the wavelength of the light coming in. We can also change how bright the light coming in is in our at least idealized experiment here. When that light strikes the metal, it turns out we can see electrons leaving the surface of the metal, okay? That's an observation all by itself. Those electrons leaving, they're electrons, so they have a negative charge on them, right? Because they have a negative charge on them, it's relatively easy to count up how many of them there are and also to measure their kinetic energies. Okay, how would we do that? Well, counting them, all we have to do is put a wire or another metal plate of some sort up above the target surface and connect that to a circuit. If enough negatively charged electrons strike that plate, a current will flow into my circuit, and I'll be able to measure that current, and that'll let me count up how many electrons that was. For the kinetic energies, if I have my electron sensor, my metal plate that's going to count the electrons, suppose I start applying a negative voltage to that. If I raise up that negative voltage, eventually that voltage would be big enough to push the electrons away so that no electrons would get there because the negative voltage on my plate would be repelling the negatively charged electrons coming towards it. Okay, so that would let me figure out what the kinetic energy of the ejected electrons actually was. A couple of experimental fudges on this or hedges on this experiment. We have to do a few things to make it work right. As I said, we have to have the whole thing in a vacuum chamber. That's not a complicated thing to do. It doesn't have to be a great level of vacuum. We need that because we don't want the electrons as they're leaving the metal to immediately crash into molecules, right? We want them to have enough chance to get to our detector before they bang into something and get deflected. The second thing I have to do is I have to ground the surface of my metal target. If I don't, then each time I knock an electron free from the metal will get more and more negative charge, and that would make it progressively more and more difficult to remove more electrons. Okay, so I have to have a closed loop circuit essentially. So my metal surface has to be connected so that it's grounded to the outside world to do that. But all of that is easy. It's an easy enough experiment that people could do it like right around the 1900 thereabouts. People start to see results from this experiment, and so it's obviously not super demanding technologically. So let's see what happens when we do this experiment. What are the results? This is a very lot of information packed into one slide. Okay, so let's look at it sequentially. First of all, I'm going to start on the top left, I guess. On the top left is the weirdest looking of these graphs, the one that looks like it's just a step upwards, right? It looks like a step function. My y-axis here says it's the number of electrons being emitted, or let's say number per second. The rate of electrons being emitted might be better, but number of electrons being emitted as a function of frequency, all right? So imagine that I can start this experiment and I start at low frequency somewhere over here, right? I turn on the light and I start raising up the frequency. For a good while, nothing happens whatsoever. The experiment is boring because no electrons are coming off. Then I hit some magical frequency, what I've labeled here as nu sub 0. At that point, my number of electrons shoots up and then I go to another plateau. right? So that says frequency is kind of a yes or no variable here, right? The frequency is either high enough or it's not high enough, all right? And in each one of these graphs, whatever is not the variable on the x-axis, so when I'm doing the frequency graph here, I'm assuming that I have the brightness or the intensity of the light held constant, okay? One other thing that turns out to be somewhat unusual about this graph is if I changed what metal I shot the light at, so if I took out my metal target and replaced it with a different metal, this nu zero here will move around. So that nu zero is a property of what specific metal I'm using in the experiment. Okay, so somehow that's telling me something about the metal itself. If I go down here on the bottom, I've still got frequency on the x-axis. Now I've got the kinetic energy of the electrons on the y-axis, okay? Below mu zero, I can't measure the kinetic energy because there are no electrons coming off, right? So I really have no graph whatsoever down here. But then once I hit mu zero, as electrons start to be emitted, they start off being emitted moving very slowly, very small kinetic energy. But as I raise the frequency, the kinetic energy goes up, and it goes up in a linear fashion. So I get this graph here, which is very much a line, okay? Now I go to the right side. I've got two graphs that both have intensity on the x-axis. How bright is the light? Okay. The top one is, again, looking at the number of electrons being ejected. Again, the two graphs on the right here are both for frequencies that are above nu zero. So I have to pick a frequency and stay at it, and it has to be above nu zero because otherwise nothing happens. I don't have anything to plot in that case, right? If I turn the intensity down to zero, that means I turn the light off. No surprise, the number of electrons goes down to zero. If I raise that intensity, start dialing up the total amount of energy I'm shooting at the surface, my number of electrons goes up linearly, okay? Kinetic energy of the electrons, on the other hand, somehow manages to be independent of the brightness of the light. Okay, this is just a flat line. It says as long as the frequency doesn't change, the kinetic energy doesn't change. So this set of graphs is very much not what people thought should happen in terms of the folks that were doing these experiments. Remember, they thought about light as being described by a wave model, right? In a wave description of light, the thing that corresponds to how much energy the light has is really the amplitude, right? That's the brightness, the graphs that are on the right-hand side of our slide. But the thing that controls the kinetic energy of electrons, according to this, is the frequency of the light, or what color the light is, okay? In a wave picture, that frequency is not at all correlated to how much energy the light would have. Yet that seems to be what dictates how much energy the electron that's ejected ends up with, okay? This part that says it doesn't matter how bright the light is if I'm down below this nu zero, right? In that range, no matter how bright I make the light, I don't get to see electrons being ejected. That's also kind of strange, right? Over here, I make the light brighter and brighter. I'm shooting more and more energy at my metal, but somehow my electrons don't get any faster. I knock off more electrons, but I don't get them to move any faster. Okay, so there's a lot of things there that really baffled the folks who were trying to think about how this could make sense with a wave description of light. The way to resolve this, it turns out, is to embrace the photon idea. Okay, and so let's look at this. Einstein actually won the Nobel Prize, not for the theory of relativity, but for describing this photoelectric effect experiment in terms of photons, okay? So that idea, that photon idea was floating around a little bit in a couple of other places. Einstein applies it to this, and that really helps it begin to get some traction. Okay, so remember, in the photon picture, what happens? I have my E equals h nu. That's the energy of a photon, right? Let's go back to the graphs for a second. Okay, remember the photon energy is E equals h nu. So if I'm down here below nu zero in this window, the energy of my photon is smaller, right? So that says when I get to nu zero, somehow the energy of a photon gets to be enough that that one photon is going to be what kicks that electron out of the metal. Okay, so what's happening here is that one photon is knocking out one electron. If I'm right at nu zero, my one photon uses all of its energy to extract the electron, and so my kinetic energy is very, very close to zero, right? But if I raise up the frequency when I'm out here, now I have more energy in my photon. The extra energy that the photon has above whatever it takes to pull the electron free from the metal, that's what turns up as the kinetic energy. So that sort of describes what's happening over there. What about the intensity? In the photon picture, the intensity corresponds to the number of photons, say number of photons per second. Right. Remember, I did that calculation towards the end of the previous video that figured out how many photons per second were coming out of my laser pointer. All right. So when I say raise the intensity, that says more photons. If I shoot more photons at the metal, well, it can eject more electrons. So this thing goes up because as the number of photons coming in goes up, the number of electrons going out will also go up. Down here, the kinetic energy doesn't depend on the number of photons because each electron that gets ejected just by one individual photon. Okay, that's the key to explaining this, is that it's the work of an individual photon that manages to knock that electron out of the metal and free it. Okay, from the fact that I don't see any electrons down here, it implies that I can't collect up like several small energy photons and add them up to get enough energy to eject an electron. That process doesn't seem to actually work. That's why I don't see electrons down there. So it's what we could describe as just being a one photon process. Okay. What else can we do with this? I mentioned, I'm sorry, I keep flipping back and forth. I mentioned that this new zero slides around as I change what metal I'm shooting in there. That means if I just change from one metal to another, I'll be able to measure which metals hold on to the electrons more tightly, which metals have a looser grip on their electrons. From a chemistry standpoint, that's interesting. That's telling me things about atoms of different elements, right? How tightly attracted to those, how strongly bound are the electrons to those different elements. And I can learn that by doing this experiment. All right, so let's move on and see what we can calculate with this, all right? One of the things we can calculate is we can measure what is known as the, we can call the binding energy in our chemistry book, okay? If you ever learned about this in a physics class or ever do learn about this in a physics class, what I'm calling a binding energy right now, a physics book would tend to call a work function, okay? Those are the same thing, just in different language. It says light with a frequency of 1.3 times 10 to the 15th hertz ejects electrons from cesium metal. If the kinetic energy is that number there, what is the binding energy of electrons in cesium metal? And it gives me a hint down there. It says conservation of energy. So let's develop a plan for solving this problem before I go to the next slide and actually solve it, okay? I like to think about this as a before and after. Before the event takes place, I have a photon, right? So the energy of my photon is equal to h nu, right? That's the energy the photon originally has. When this process takes place, when the electron is ejected, the photon is absorbed by the metal, so the photon essentially is destroyed. I don't have that light anymore, right? So the energy from that light has to go someplace, right? Some of that energy is going to become the kinetic energy, this piece here, right? The rest of that energy is going to be the amount of energy it takes to do work to pull the electron free from the metal, okay? The metal doesn't just spit out the electrons on its own. If I don't shoot the light at the metal, then the electrons don't come out. The metal wants to keep the electrons, okay? So it costs me energy to tear the electron free. If I was teaching physics, I would say something about the work energy theorem as saying that the amount of energy it takes there is the amount of work I have to do to pull the electron free, okay? That amount of energy is what in my problem statement I called a binding energy. So this is my working statement for what's going to happen, right? The energy of the photon ends up, we can account for that by looking in two places. Some of it is the kinetic energy, the rest of it is the binding energy. Okay, let's actually calculate that binding energy now. The equation I just had says what? Says h nu is equal to, I'll write it as the binding energy plus the kinetic energy. That tells me that my binding energy is equal to h nu, the photon energy, minus the kinetic energy. That's equal to h, which is 6.626. times 10 to the minus 34th power. That's in joules seconds. My frequency is 1.3 times 10 to the 15th inverse seconds. And I'm adding to that, I'm subtracting from that 5.2 times 10 to the minus 19 joules. I wrote out notes here that say this piece, my photon energy here is 8.6 times 10 to the minus 19 joules, minus that 5.2. And that says that if I subtract those, it's not that hard to say we get 3.4 times 10 to the minus 19 joules, right? So this is my cesium binding energy. That tells me it costs me that much energy to tear an electron free from the surface of the cesium metal, okay? If I repeated this experiment with a different metal, I would get a different answer for the binding energy. I will tell you that cesium is on the very low end of the list of these binding energies for different metals. So if I tried another metal, I would get a higher binding energy than that. Also notice something else about that binding energy. You'll see here this 10 to the minus 19 joules as the order of magnitude, right? Remember, that's the typical order of magnitude of a photon of visible light. And so that's kind of another pointer to why light is important as a probe of atoms and molecules. It's because the energies of photons are about the same size as the energies that we associate with those atoms and molecules. Again, that makes light a very, very good probe for learning things about our atoms and molecules.